Good morning students, this is Shilpa teacher. In our last session of Science 1, we have started our first chapter, gravitation. Before starting today's session, just I will revise what points we have learned last time. Gravitation. Gravitation is attractive force exerted by all the elements or all the objects in the entire universe, and this force is attracting each and every object towards them. This force is discovered by Sir Isaac Newton. Next, centripetal force. Centripetal force is the force which is essential for circular motion. This force is directed towards the center of circle, and that's why the name is centripetal, that is center seeking. Next, Kepler's 3 laws of planetary motion. Out of that 3 laws, first law was the orbit of planet is an ellipse with sun at one of the foci. Kepler's second law states the line joining the planet and sun sweeps equal areas in equal intervals of time. And Kepler's third law states the square of its period of revolution around the sun is directly proportional to the cube of mean distance of the planet from the sun. Next point was Newton's universal law of gravitation, which states that every object in universe attracts every other object with a definite force. This force is directly proportional to the product of masses of the two objects and is inversely proportional to square of the distance between them. Next point we have learned was inverse square law or magnitude of centripetal force. By taking help of Kepler's third law, Newton proved inverse square dependence of distance between two objects. And magnitude of centripetal force is given by F is equal to mv square by r. Next is Earth's gravitational force. Like all other objects in the universe, Earth is also having its own gravitational force. And due to this gravitational force, acceleration is generated. That acceleration is known as Earth's gravitational acceleration. Variation in the value of g according to changing surface of Earth, height and depth. These all points we have learnt in last session. Now we are going to start our today's session. So we will start with our today's session with the point mass and weight. What do you think? Mass and weight, these both things are same? Answer is no. Why they are different? When we will learn this, you will get to know. So first we will focus on mass. Mass can be defined as it is the amount of matter present in the object. For example, consider here are 2 cups. In first cup there is 2 kg sugar, and in second cup it is filled with 4 kg sugar. So the mass of first cup is 2 kg and mass of second cup is 4 kg. That is what it indicates. Inside this cup, what is the amount of sugar is present? That is nothing but its mass, and that is 4 kg. This cup is small in size, so it contains small mass, and that mass of sugar is 2 kg. Means every object in the world, inside that whatever is present, that matter, what it amounts total is called as its mass. Second is the SI unit of mass is kilogram. Means mass is measured in terms of kilogram. kilogram is SI unit. Smaller unit for mass is gram. Next, it is a scalar quantity. Why? Because, for example, suppose this cup, if I will keep in each direction, its mass will be 4 kg. If I will keep in west direction, its mass will be again 4 kg. Means in any direction, if I will keep these cups or any object, the matter inside that is not going to change. That is, it is not dependent on direction. So it is a scalar quantity. Next, its value is same everywhere. How? For example, again consider this cup of sugar. If you will keep this cup of sugar anywhere in the world or out of the world also, suppose this cup you are going to keep on moon or any other planet, will the content of sugar in that cup is going to change? No. The amount of sugar in that cup will remain same. That is nothing but its mass will remain same. That's why value of mass is always same everywhere. Next is, it is a measure of inertia. Inertia in 9th standard you have learnt. Inertia, it is the tendency of object to remain in position in which it is belonging. Higher is the inertia, higher is the mass. So, mass is nothing but amount of matter present in the object. Now we will see what is meant by weight. Weight can be defined as gravitational force acting on the object. We know that Earth is applying gravitational force on every object. For example, consider the same 2 cups filled with sugar. One is filled with 2 kg sugar and second is filled with 4 kg sugar. As this second cup is having higher mass than first cup, gravitational force acting on this is more and gravitational force acting on this is less. So weight of second cup filled with 4 kg sugar is more than first cup. Now SI unit of weight is Newton. It is a vector quantity. Why? Because weight is nothing but gravitational force and this force is directed towards the center of Earth. As it is having direction, this gravitational force is having direction. That's why weight is also needs direction. So it is a vector quantity because it is expressed with the help of magnitude and direction both. That's why it's a vector quantity. Next, it is not same everywhere. Reason for that will be cleared with this formula. Weight is nothing but gravitational force acting on the object. So it is the force, and force we know that it is given by formula mass into acceleration. Just now we have seen that mass is not going to change, it is remaining constant. Acceleration is the acceleration produced by gravitational force of Earth. That's why this acceleration can be replaced by small g. So the weight is nothing but gravitational force acting on the object. So it can be given by this formula mass into acceleration due to gravity. Now if you will see this formula, mass is constant. So this weight or force is directly just dependent on acceleration due to gravity. And we know that acceleration due to gravity is not constant, because in last session we have seen it is going to change according to depth, according to height, and according to surface also it is going to change. This gravitational acceleration is not remaining stable, and as this is the variable thing, gravitational force is varying, and that's why weight is varying. So weight is not remaining same everywhere, it is going to change place to place. For example, suppose this is the object which is present on the surface of Earth. On the surface of Earth, its weight is 60 Newton, and that same object now if placed on Moon, its weight will be 6 Newton. Why this is so? Because we know that Moon's gravitational acceleration is 6 times less than Earth's gravitational acceleration. That is, it is smaller than Earth's gravitational by factor 1/6. That's why 60 divided by 6, answer will be 6 Newton. 6 times less weight of the object will be there on Moon. In this way, the object shows different weight on different planets. In our daily life or in general, we are using mass and weight as the same quantities. For example, suppose I will ask you question, what is your weight? Suppose you told answer 75 kg. But actually kg is the unit of what? Mass. Just now we have learned. So when I am asking you what is your weight, actually you are telling your mass. In scientific language, when we say that my weight is 75 kg, actually we are talking about our mass. What we mean is that my weight is equal to gravitational force on 75 kg mass. As my mass is 75 kg, my weight on the earth is calculated in this way. Weight is equal to mass into acceleration due to gravity. As mass is 75 kg, acceleration due to gravity value, we know that it is 9.8. So its value will be 735 Newton. So actually when we are telling my weight is 75 kg, we are telling our mass, and that time our weight will be 735 Newton. That is, this is the gravitational force applied by Earth on my body. So that will be weight. Our weighing machines tells us the mass. The two scale balances in shop compare two weights, that is two masses. So in generally, weight and mass we are using as the same quantity, but actually in scientific language these two terms are different. Mass, its unit is kilogram, and weight, its unit is Newton. This is the amount of matter present in the object, and it is the gravitational force acting on the object.
Let's accept it. Most of us think that mass and weight are pretty much the same thing. Are they? No, they're not. There's a very simple way to understand the difference. Mass is simply the amount of matter that's present in the object. Now consider two situations. One in which an object is on the Earth, and second in which the same object is on the Moon. Will the mass of the object be different in these cases? To answer this question, we ask ourselves another simple question. Will the amount of matter present in the object be different in these cases? Absolutely not. The matter in the object is not changing at all, which is why the mass will be the same in each of the cases. The mass of an object remains constant no matter where it is placed. The standard metric unit of mass is the kilogram. Another concept we'd learnt about an object's mass was that it is a measure of its inertia. Greater the mass of an object, greater will be its inertia. Inertia is nothing but the tendency of an object to resist change in its state of motion. So now we have an idea about what mass is. But what's weight then? How do we understand the weight of an object? Mass is nothing but the measure of how much matter an object has. Weight is a measure of how strongly gravity pulls on that matter. It's the measurement of the gravitational pull of an object. Let's understand this using a simple example. Say there are two places, place A and place B, and there's an object of mass m. In place A, the pull of gravity is x units, and in place B, the pull of gravity is 2x units. Clearly, the pull of gravity is stronger at place B. Now understand this well. The mass of the object will be m at both the places, but the weight of the object will be greater at place B because the pull of gravity is stronger. As the gravity is twice as bigger, the weight of the object will be twice as much at place B as compared to place A. So the weight of an object is a measurement of gravitational force acting on it. How can we understand weight using a formula? We know the Newton's second law of motion, which says that the force acting on an object is the product of its mass and acceleration. When it's acceleration due to gravity, we can replace A with a lowercase g. This force due to gravity is nothing but the weight of the object. So if we consider the weight of an object to be uppercase W, we can rewrite this equation as W equals m times g. So the weight of an object is the product of its mass and acceleration due to gravity. What will be the SI unit of weight? Can you guess? It'll be the same as that of force, Newton. As the value of g at a particular place is constant, we can also say that the weight of the object is directly proportional to its mass. Here's the main takeaway from this video. The mass of an object remains constant everywhere, whereas its weight depends on the gravitational force at the location.
Now, let us differentiate between mass and weight. First point of difference is definition. Mass is the amount of matter present in the object. Weight is the gravitational force acting on the object. Next point is effect of gravity. Mass always remains same everywhere and anytime. Weight of the object depends on gravity at that place. Next point of difference is type of quantity. Mass is scalar quantity. It has only magnitude. Weight is vector quantity. It has magnitude and it is directed towards the center of earth. Next is devices used for measurement of mass. Mass can be measured using pan balance, triple beam balance, lever balance or electronic balance. Weight can be measured using spring balance. Next point of difference is value. Mass can't be zero, whereas weight can be zero if there is no gravity, for example space. Next is unit of measurement. Mass can be measured in units gram, kilogram or milligram. Weight is measured in unit Newton. Our next point is free fall. To understand free fall, let us do one activity. Take a small stone, hold it in your hand. Which forces are acting on this stone? Yes, we know that the force of gravity due to Earth acts on each and every object. When we were holding the stone in our hand, the stone was experiencing this force. But this gravitational force of Earth is balanced by equal and opposite force applied by us. And that's why these two forces, means the gravitational force acting on the object due to Earth and the force acting on that object by us, these two forces are acting in opposite direction, so they cancel each other, and as a result the stone remains at rest. Now release the stone. What do you observe? What are the forces acting on the stone after you release it? Once we release the stone from our hands, the only force that acts on it is gravitational force of earth, and the stone falls down under its influence. In this way, whenever an object moves under the influence of gravity only, then it is said to be falling freely. Thus, when we release the stone, it is falling only under the influence of gravity, and so it is falling freely. But true free fall is possible only in vacuum. Why? Because whenever any object is coming down towards the earth, surrounding that object atmosphere is present, and due to that frictional force of air opposes the motion of the object. Also, the buoyant force acts on the object. Due to these two opposite forces, free fall is not possible in atmosphere. But in vacuum, there is no air, so no frictional force, no buoyant force. Only the gravitational force will act on that object, and that's why the free fall truly is possible only in vacuum. With the next video, you will get to know that.
Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. TCV 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Exactly. They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing.
Look at that.
So in this video, you have seen that when the feather and ball dropped in presence of atmosphere, the feather has come down slowly as compared to ball, and in second attempt, when the air is removed and vacuum is created, we have seen that feather and ball, they both are coming at the same speed towards the earth. Though the feather is very light and ball was heavy, then also the speed of falling of both the object was same, because here presence of vacuum was there, and that both feather and ball was falling under only the influence of gravity. So they both were in free fall. In this way, the true free fall is possible only in presence of vacuum. Now, during free fall, initial velocity of the object remains zero. For example, consider the stone. Here the initial velocity of the stone was zero. When I will release that stone, the velocity goes on increasing as it goes towards the surface of earth. Now, for a freely moving body, we will try to obtain equations for velocity and displacement by using Newton's three laws of motion or three equations of motion. Newton's first equation of motion is V is equal to U plus AT. Second equation is S is equal to UT plus half AT square. And third equation of motion is V square is equal to U square plus 2AS, where V is final velocity, U is initial velocity, A is acceleration, and T is time taken. S is the displacement. Just now we have seen that for freely moving body, initial velocity always remains zero and the acceleration becomes acceleration due to gravity. Why? Because here only gravity is acting on that object. So acceleration becomes acceleration due to gravity. Just these two values we will put in these equations and we will get equation for freely falling object. Just put that values in first equation. V is equal to U is 0. So 0 plus A becomes GT. So V is equal to GT. This is the equation for freely falling object. Next is S is equal to U again 0. 0 into T 0 plus half. A will become G T square. So this term will become 0. Only just remain half GT square. So second equation will be transformed into this. And next V square is equal to U will become 0 plus 2 instead of A G S. So V square is equal to 2 GS. This will be third equation. Here just one thing you remember, acceleration due to gravity is positive here because the object is falling downward towards the center of earth. But if the object is moving upward, then acceleration due to gravity G will become negative. This is for upward direction. Why? Because in that case acceleration due to gravity will be negative because it will oppose the velocity. That's why it will become negative. So accordingly we have to make the changes in the equation. It will become minus GT. Here it will become minus GT and here also it will become minus GT for the object moving in upward direction. And these three equations are for the object moving freely towards earth. The moon and artificial satellites are moving only under the influence of gravitational field of earth and thus they are also in free fall.
Free fall. Try this. Take a small stone. Hold it in your hand. Which forces are acting on the stone? Now release the stone. What do you observe? What are the forces acting on the stone after you release it? We know that the force of gravity due to the earth acts on each and every object. When we are holding the stone in our hand, the stone was experiencing this force, but it was balanced by a force that we are applying on it in the opposite direction. As a result, the stone remained at rest. Once we release the stone from our hands, the only force that acts on it is the gravitational force of the earth, and the stone falls down under its influence. Whenever an object moves under the influence of the force of gravity alone, it is said to be falling freely. Thus, the released stone is in a free fall. In free fall, the initial velocity of the object is zero and goes on increasing due to the acceleration due to gravity of the earth. During free fall, the frictional force due to air opposes the motion of the object, and a buoyant force also acts on the object. Thus, true free fall is possible only in vacuum. For a freely falling object, the velocity on reaching the earth and the time taken for it can be calculated by using Newton's equations of motion. For free fall, the initial velocity u is equal to 0 and the acceleration a is equal to g. V is equal to gt, s is equal to 1 upon 2 gt square, that is half gt square. V square is equal to 2gs. For calculating the motion of an object thrown upwards, acceleration is negative, that is, in a direction opposite to the velocity, and is taken to be minus g. The magnitude of g is the same, but the velocity of the object decreases because of this negative acceleration. The moon and the artificial satellites are moving only under the influence of the gravitational field of the earth. Thus, they are in free fall. Do you know? The value of g is the same for all objects at a given place on the earth. Thus, any two objects, irrespective of their masses or any other properties, when dropped from the same height and falling freely, will reach the earth at the same time. Galileo is said to have performed an experiment around 1590 in the Italian city of Pisa. He dropped two spheres of different masses from the Leaning Tower of Pisa to demonstrate that both spheres reached the ground at the same time. When we drop a feather and a heavy stone at the same time from a height, they do not reach the earth at the same time. The feather experiences a buoyant force and a frictional force due to the air and therefore floats and reaches the ground slowly, later than the heavy stone. The buoyant and the frictional force on the stone are much less than the weight of the stone and do not affect the speed of the stone much. Recently, scientists performed this experiment in vacuum and showed that the feather and stone indeed reach the earth at the same time. Use your brain power. According to Newton's law of gravitation, Earth's gravitational force is higher on an object of larger mass. Why doesn't that object fall down with higher velocity as compared to an object with lower mass?